Welcome to this Infinity Talk, presented by Ocean Infinity. Today's talk is by safety engineer and AI expert Rocco Van Schalkwyk, and the title is, Can Machines Have Emotions?
So hello and welcome, everybody. My name is Rocco Van Schalkwyk, and I would normally be talking to you about safety engineering and design compliance of our robotic ship and subsea asset development programs. But today I want to talk to you about the robots that I built after hours to keep me off the streets, so to speak. The title of my talk today is, Can Machines Have Emotions? Now, before I start, I would like to thank the OI Employee Engagement Committee, specifically Jake Madsen, for arranging this Infinity Talk, and also my boss, Simon Crompton, for making this time available so that I can speak to you today while he comes up with the next impossible task for me. Just kidding. Simon knows I like impossible tasks. This is quite a lengthy slide deck, so if you don't mind, can we keep the questions for the end? Thank you. So, can machines have emotions? If you told me 30 years ago that machines can have emotions, I would have been out of here in 5 seconds. And I would have written you off as a crank, as a stoner, as a nutter. But for the past 30 years, I've been working on AI and a brain model for autonomous robots. A model that can give robots both emotions and intelligence similar to humans. I started a small collaboration group of engineers and neuroscientists called the Xzistor Lab, and I called my brain model the Xzistor Mathematical Model of Mind. And using aspects from this Xzistor brain model, I hope to convince you today that machines can have emotions, subjectively felt emotions that are principally no different from those experienced by humans, only in another substrate. I've broken the content of this talk down into 7 sections today. So we'll briefly look at the sensors for robots. We'll talk just about motor commands for robots. We'll need to talk about drives for robots. And then we'll get to the core business of emotions for robots. I'll also dive into 1 or 2 of these specific emotions like pain, stress, and anger. And then we'll do a comparison of the Xzistor model with a biological brain. And I'll also just talk a little bit about consciousness at the end because I know people are interested in that topic. So let's start with sensors for robots. And we look at a tactile sense first, basically just a fancy word for a sense of touch. And I want to start off on a very simple note by looking at a basic spring-loaded push button. As we push it, it can register 3 levels of pressure: soft, medium, and hard. We can easily turn this into a touch sensor. We simply attach it to a potentiometer and use an analog to digital converter to write the current voltage value into a table. Let's say it can take a value of 0, 1, 2, or 3. And we can extend the tactile table to reflect all the sensors with their current readings. To provide a hard-shelled robot with a smoother tactile sense, more like humans have with their flexible skins, we build a simple rule into our tactile table, which says pressure on one button will have an effect on the sensors next to it. The touch sensors around the sensor number 18 are not being touched, but they are assigned readings based on their proximity to number 18. And this is what I call the neighbor effect. And we will see later why it's really important for our discussion on the brain. And there we see if less pressure is exerted on sensor number 18, the effect on its neighbors is also limited. Remember, this happens in the table. The buttons around sensor 18 do not move. We can now place touch sensors all over the rest of the robot's body. By adding more tactile sensors around the body of the robot, we can turn our tactile table into a body map. In the end, it's just a bigger table. No tactile sense yet, just a table. We can use isolators to split up areas in the body map to limit the neighbor effect. For example, touching your upper lip is not really felt in your lower lip. I hope with this simple trick, I will blow your socks off later in this talk, so stay tuned. By using integrated microsensor arrays inside a Xzistor robot, we can build a body map required for synthetic exteroception and interoception. Let me explain these two big words. Exteroception, the red sensors, are sensors on the outer shell or skin of the robot. Interoception, the amber sensors, are sensors inside the robot body. And these days you can buy a myriad of integrated microsensors, as we will see in the next slide. These include thermosensors, barosensors, chemiosensors, accelerometers, microstrain gauges, vibration sensors, and many more. To provide a robot with a highly refined tactile map, very sophisticated solutions are available today. Like this one called eFlash. I'm just going to see if I can play the video for you. And you'll clearly see how by just touching that part of the eFlash structure, you create those tactile maps. You can see it on the right-hand side very accurately. So this we can cover a whole robot and build a tactile sense like that. In the end, we rely on minute transistors in the silicon wafers of the robot's brain to turn sensor measurements into numerical representations. But remember, this is not a tactile sense yet, just a spreadsheet. The yellow sensors inside the robot that create the internal body map will become important for our discussion on emotions. To eventually move the discussion to emotions, we do have to quickly show how other sensory measurements can also be turned into numerical representations. Let's take a look at a visual sense for robots. Simple enough, we know video frames can be broken down into pixels and turned into RGB tables. And there you see an example of an RGB table as a numerical representation of a frame. Similarly, we can also look at an auditory sense for robots. Using a sound spectrum analyzer, we can turn audible sounds into numerical representations, like for the word feel. The spoken words are just pressure waves that the microphone passes to the frequency spectrum analyzer, which can digitize it and turn it into a numerical representation. This is an actual digital spectrum analyzer we use at the Xzistor lab, and it shows the pattern for when I said the word feel into the microphone. Again, we are just explaining the basic principles here. And this is me saying the word hand. Of course, this will be set to a much higher resolution for actual robotic applications. We said we will have a little talk about motor commands, and I just want to, again, explain the simple principles the Xzistor model use when it comes to motor commands. So here, the robot brain will make decisions that will result in motor commands. We are just going the other way, from numerical representations to electrical signals for the motors and actuators, using digital to analog converters. So let's recap. We have looked at 3 sensors, and of course there are many more, and motor commands. But these are not sensors or contemplated actions yet, just tables with numbers in them. These are just numerical representations of sensor signals and digital values that command the motors. The problem is that these numerical interpretation tables of changing sensor measurements are not interpreted by anything. They are stone-cold spreadsheets, as sentient as a stop sign. We need a captain for our ship, something that interprets these incoming states and do something about it. Let's take a look at what such an interpreter or executor should do. Let's ask ourselves, what can the executor do with the incoming information to decide what action should be taken? The executor can start to save associations to an association database by taking snapshots of what states are coming in at the same moment in time. The value of this will soon be apparent. How can it save such an association or a snapshot? By first putting these numerical representations into an association buffer and then saving it to an association database like we have on this slide. Now, the executor algorithm can use incoming information in the form of numerical representations to base appropriate actions on. Assume we make the executor algorithm cycle through the latest incoming sensory tables: tactile external, tactile internal, visual, audio, and motor, as they get updated in real time. And there we see the cycle, what we call the Xzistor logic loop. The Xzistor performs this loop over and over again to see what new information is coming in and what actions it should perform. It starts with 1, reading incoming numerical representations, then moves to step number 2, where it moves these representations into the association buffer. Step number 3, it will compare the association buffer content with the association database and either store or update associations. Number 4, it will decide actions and create numerical commands for the motion effectors, the motors and the actioners. And then it'll perform those actions. And then immediately it'll go back as part of the logic loop and start reading the incoming representations again and go around the loop in that fashion. Isn't this great? No, it's not. Why not? What would make the executor choose certain motions? What would motivate it? What would its mission be? And it's time to talk about drives for robots. We can give the robot a mission. Let's go back to a simple robot that runs on battery power. The robot must keep its battery charged and make sure it doesn't drop below 15% at any time, else this could happen. We can pre-program it to search for a green wall socket and then navigate to it when its battery drops below 15%. This, of course, will just be an instinct. It will require no thinking. But the robot will not learn to navigate to other wall sockets that might look different. It will only be pre-programmed to recognize one specific shape and color. And we can do better than this. Let's help the robot navigate to different wall sockets and then make it learn which wall sockets actually provide power. How do we do this? We reward any correct attempt to find a charging wall socket with memory reinforcement. And there you see the tutor helping the robot along in the direction of the wall socket. This graph shows how the battery level gets depleted over time, and then how it gets charged once connected to the blue wall socket. The urgency to restore the battery level moves up from non-urgent to very urgent, and then as it is charged, the urgency drops again as it moves towards the ideal battery level, as what we call the set point. Just a few important terms to aid our discussion. The rising part of the curve in red, where the battery gets depleted and the urgency to restore the battery power gets more urgent, we will call the deprivation phase. The part of the curve in green that drops down once a charger has been found is called the satiation phase. The inflection point on this graph is extremely important. In Xzistor speak, we call this the satiation event. On this very moment, the declining battery charge level changes from decreasing to increasing. And this is what we want the robot to learn. Like I said, the satiation event is very important in the Xzistor brain model. A few things happen simultaneously exactly at this moment, and their numerical representations are recorded in the association buffer. Firstly, the robot sees the blue wall socket. Secondly, it feels the plug being pushed into the wall socket with its hand. Thirdly, it hears the words blue socket. Fourth on the list, its motors perform actions to position and push the plug into the socket. Last but not least, the state created by the robot's internal sensors are registered from the internal body map. We can reinforce the sensory states and the current motor actions when we turn them into an association, which we store in the association database. Reinforcement simply means that when in future the robot's battery drops below 15% and it sees a blue wall socket, it will recognize the socket from the association database and try these reinforced motor actions to try and get the plug into the socket and avoid the battery from dropping below 15%. The robot can potentially now start to learn avoidance behaviors. Just remember that all the states the executor are presented with are still just numerical representations, digital spreadsheets, and the motor commands going out from the executor to the motors are also just numbers. This is nothing other than a negative feedback control loop that aims to maintain the battery level at a preferred state or set point. We say it tries to maintain homeostasis. What is homeostasis? No better example than to look at the thermostat. Let's assume it is tasked with keeping a room at a comfortable temperature. If the temperature rises too high, it switches on the fan. If the temperature drops too low, it switches on the heater. This keeps the room at the preferred temperature. This is what we mean with maintaining homeostasis. We can use the reinforcement of homeostatic actions to teach a robot to avoid many unwanted states. For example, we can teach a robot to avoid getting too cold or getting too hot. We can even let it learn to avoid damage, pain. How do we do this? We can make the robot learn to avoid a too cold environment by reinforcing actions that avoid cold environments. Here the tutor tells the robot to move to the kitchen where it is warmer. When the robot feels the temperature improving, it experiences a satiation event and learns what to do in future. Similarly, we can make the robot learn to avoid a too hot environment by reinforcing actions that avoid overly hot environments. Again, the satiation event will teach a robot to dial down the heating when feeling too hot in future. We can even provide the robot with a homeostat for pain by using our push button and adapting it to measure very high pressures that can generate pain signals. For mere touch states, we had soft, medium, hard. Pushing even harder, we can use the signals to signify light pain, medium pain, and extreme pain. Same sensor, but the amber part is the sensory signals, while the red part is the homeostatic signals, which the robot will learn to avoid. We will teach a robot to move away from the source of severe pressure, pain, in order to avoid feeling pain in future. And as the pain stops, the satiation event will occur, and the robot will learn to stay away from the red boxing glove. We have shown how we can let the robot learn to avoid pain, avoid feeling too cold, avoid feeling too hot, and a sensation of battery depletion akin to how humans might feel hunger. We can provide the robot with synthetic versions of many of the biological homeostats in the human body. These homeostatic mechanisms in our robot brain can perhaps underpin emotions? The Xzistor brain model suggests we might be on the right track. And now we get to the core business for today, emotions for robots. The Xzistor mathematical model of mind defines an innate emotion as any somatosensory state a human can become aware of, for which he/she can self-report that it felt bad entering the state and felt better leaving the state. Examples are cold, heat, pain, acute fear, hunger, thirst, anger, sexual arousal, bladder discomfort, defecation discomfort, itch, extreme noise, anxiety, separation stress, autonomic stress, muscle tension, fatigue, nausea, and many more. Sexual arousal, really? Robot orgasm? I can't go into this without verifying your ages. Well, at least those that are in the UK. But you can read how we do this on the provided Xzistor Lab website. We will actually run a simplified model of the brain's limbic system to achieve that. Again, all the links will be on the last slide if you are interested. With the Xzistor brain model, we can mathematically model these homeostatic emotions in robots. No, not model, rather principally replicate them, just using another inorganic substrate. We can now give the robot many different missions. We can give it things to care about, things to pursue, and things to avoid, so that it can survive and learn to protect itself from damage. This could motivate the robot and will give meaning to objects it observes in its environment. Isn't that great? No, it isn't. We have a fundamental problem here. What is the problem? The executor is not aware of these homeostat states. It will not know when the battery level is dropping, causing deprivation, or when charging is commenced, causing satiation. All the executor sees are the numerical representations from the sensory inputs and the motor commands table it generated. Look again at what we said it is presented with. Our executor is only aware of the changes in the numerical representations for the external body map, the internal body map, the visual sense, the audio sense, and the motor commands. We see no homeostat states in the association buffer. How do we make the executor aware of the many different homeostat states, including when they are in deprivation or when in satiation? We need to change the homeostat states into numerical representations that the executor algorithm can read and assess too. This can help the executor learn and make decisions to accomplish its missions. This is where the Xzistor brain model offers a unique feature you will not find in any other brain model. Instead of simply making the homeostat signals changes available to the executor as new numerical tables, the Xzistor brain model embeds these into the existing internal and external sensory representations. We choose an area of the body map that will not cause confusion, the intra-abdominal area that we have called the internal body map. We simply expand and embed the homeostatic states into the part of the body map we have reserved for the intra-abdominal areas. It's almost like we hijack some real estate in the internal body map to house our little homeostat factory. From a sensory perspective, the intra-abdominal and inner trunk area of the body do not require highly defined sensory perception, not like the fingers, the feet, the mouth, the lips. It can thus be used to pass other important information to the robot brain. Bodily feelings not originating from the internal sensory states, but derived from the internal homeostatic states. It's important to remember that the numerical representations of the homeostats that feel like internal sensory states, interoception, are actually generated from homeostat control variables and not sensory signals. The homeostat signals are for teaching a robot to perform actions, not just to perceive and recognize stimuli from the environment and body as the rest of the body map. And just look at what I did here. I rejigged the body map a little by moving the head down. This again is to blow your socks off later in the talk. See, we'll get to that bit. These homeostatic states that parasiticide, if I can just pronounce that word, on the internal body map almost make me think of the cuckoo that lets other birds raise its chicks. But it's a clever trick by the brain, as we will soon see. Look at the verbs the Xzistor robot will learn to use when referring to the states experienced in the internal and external body map.
I feel this. For audio, I hear this. For visual, I see this. And for motor, I do this. Very important in red above, the robot will also learn to say I feel when referring to the numerical representations of homeostats, because they reside within the body map and are therefore experienced as feelings too.
Now the association buffer contains crucial homeostat information that the executor can read and assess to decide what it wants to do. If we look at the green arrow, we see how the robot brain can reinforce actions that move an urgent homeostat from a feeling associated with deprivation to a feeling associated with satiation. It tells the robot to always avoid feelings of deprivation and always pursue feelings of satiation. As the robot learns more words, it could learn to call deprivation feelings bad and satiation feelings good. That's, of course, if it speaks English. And the executor can make sure, as it performs its logic loop, it prioritizes homeostats that are the most urgent, those that are the highest in deprivation. This will ensure it always focuses on the most important aspects required for the robot to survive and thrive. Did we say Xzistor robots can be taught to speak? To say words and sentences? Yes, they can. Read about our latest project at the Xzistor lab, where we teach an infant robot to speak in the same way a baby learns. Let's take stock.
We've given our robot motivations. The executor will learn to avoid and pursue body felt states created by homeostats. Remember, the executor never sees the raw sensor measurements, only numerical representations of it. And there you have it. The robot's emotions are exactly these homeostat states that have been turned into body feelings and which the robot learns to avoid or pursue. This could lead an Xzistor robot to saying, I do not like this feeling of a depleted battery. I need to do something to find a charger. Charging my battery will make me feel good. Is this principally how human emotions work too? We will do a comparison later. Now I want to talk a little bit about stress, pain, and anger in robots. Using the Xzistor brain model, we can use a homeostat to build stress into a robot brain. This is a more complex algorithm that I will not discuss in detail here, but take a look at this diagram showing how we model autonomic stress. We basically provide a mathematical model of the amygdala, the hypothalamus, and the adrenal medulla, which in effect allows us to also include a model of the autonomic nervous system. The model also includes a simplified model of the limbic system, all in papers provided on the last slide. Inside our modeled amygdala, we run 3 homeostats, one for anger, one for acute fear, and one for autonomic stress. Modeling stress in a robot is incredibly important, as we will see in a minute. The stress homeostat actually creates physical effects in the gut area that can, for instance, be measured as a cold internal feeling, akin to the human version of butterflies in the stomach. With strong cooling fans, we can give a robot a cold feeling in its gut area when its stress levels go up. Why is it helpful to give a robot a stress emotion? Every homeostat emotion in an Xzistor robot also triggers a stress response. When the homeostat emotion goes into deprivation, the stress level increases. And when the emotion goes into satiation, the stress level drops. We know from the academic literature that it works the same in the human body and brain. Incorporating stress into the Xzistor brain model is interesting and crucial for creating emotions in robots. For example, assume we store a stress state with a pain state. When in future the robot recognizes the pain threat, it does not feel pain again, but it feels stress. The robot does not retreat from the threat because it feels pain. It retreats from the threat because it feels stress. So we have a rule. Stress can be recalled from memory, but not pain, just like in the human brain. This leads to a unique stress-driven way for Xzistor robots to learn reinforcement actions. As it learns to navigate to a wall socket, all the perceived objects in the environment telling it it's on the right track cannot change the robot's battery level, but it can change the robot's stress level. Every object causes a little stress-driven satiation event, which reinforces its navigation actions towards the wall socket. This is how it learns to navigate to the wall socket from further and further away. Eventually, it is stress that drives most of the subtasks the robot needs to learn to get through the day and prevent its emotions from going into deprivation. Sounds familiar? Yes, I claim the human brain principally works no different.
Here is another example where we simulated hunger in a robot. Because the hunger level cannot be changed by non-edible environmental objects en route to the red apple, it is undulations in the stress level, that is the blue line in the curve, that causes small stress satiation events. These small satiation events reinforces objects as positive cues that will show the way to the red apple in future. Just to say this is a simplification, things are a little slightly more complex than this in real life. Let's look at the emotion of anger. This is how we can enhance a feeling of anger in a robot. By heating parts of the body with heating pads when the robot recognizes a threat or getting blocked from achieving satiation. We have a blank canvas now where we can curate these emotion states akin to human emotions. Some homeostat signals will go straight to the body map, while others could trigger reflexes that add elaborate and often dynamic body sensations. Do you know who I always think of when I curate these subjective emotions for my Xzistor robots? God. Some emotions can even co-opt other emotions as they move through the body map and make for combinatorially rich and complex emotions that get tagged to objects and experiences in the association database. Some of these are crafted like symphonies, like the human orgasm. And again, the link will be on the last page. I'm sure you'll be interested. If you find it hard to believe a robot can experience rich and varied emotions like a human, meet Troopy. This is a slide I often pull out to annoy my naysayers. How many emotions can this Lego robot experience, do you think? This simple Lego robot called Troopy can experience emotions based on homeostatic and allostatic control loops. We can give it an emotion for thirst, hunger, cold, warm, fatigue, anger, stress, fight or flight, nausea, arousal, bonding, and 10 different pains experienced in 10 different body areas, 20 emotions in all. Each emotion can go from 0 to 100%, 1% at a time. For feeling bad, that is departing from homeostasis. And 0 to 100%, 1% at a time. For feeling good, the rate of restoring homeostasis. Ignoring the emotion sets that get stored to memory and recalled, how many different combinations of emotions can this little robot experience? Well, there you see it.
1 times 10 to the 42.
Still want to tell me robots cannot approach the human brain when it comes to rich and varied emotions? How many grains of sand are there in all the deserts and on all the beaches of the world? 7.5 times 10 to the 18. Even simple robots can have almost infinite number of different combinations of emotions.
Let's do a quick comparison with the human brain to see if we can see any evidence that the human brain works in the same way as I have described here. So our model needs a body map for our tactile sense. Does the human brain have something like that? Funny you should ask. The academic literature defines the somatosensory cortex. The somatosensory cortex processes sensory information from the body, including touch, temperature, pain, and pressure, and integrates it with memories and emotion to facilitate decision-making, motor control, and learning. Don't you think the resemblance is uncanny? Told you I'm going to blow your socks off. The one is a numerical representation, while the other is a neural representation. Just a difference in substrate. Does our homeostat factory seem a little far-fetched? Does the human brain have something like that? Funny you should ask. There happens to be a part of the brain called the insula at the end of that mysterious entrance to the intra-abdominal part of the body map. What can neuroscientists tell us about this area? From the academic literature, the insula plays a role in diverse functions usually linked to emotion, interoception, or the regulation of the body's homeostasis. These functions include compassion, empathy, taste, perception, motor control, self-awareness, cognitive functioning, interpersonal relationships, and awareness of homeostatic emotions such as hunger, pain, and fatigue. It is thought to play a role in consciousness too. Does the biological brain have something like an association database? Pretty close. From the academic literature, the hippocampus and the prefrontal cortex are the primary brain structures for memory and learning, though other areas also play crucial roles. The hippocampus is essential for forming new memories and transferring them to long-term storage, while the prefrontal cortex is involved in working memory, consolidating new information and existing knowledge, and retrieving memories. Is there an area in the brain that turns the decisions made by the brain into actions? There certainly is. The primary motor cortex is the main contributor to generating neural impulses that pass down the spinal cord and control the execution of movement. However, some of the other motor areas in the brain also play a role in this function. It is located on the anterior paracentral lobule on the medial surface. Finally, is there anything vaguely resembling an executor in the biological brain? The thalamus acts as a central hub for sensory information. Each sensory function has a thalamic nucleus. The thalamus is central to regulating wakefulness and awareness, and processing and regulating emotions. Through complex connections, it integrates information and plays a key role in memory storage and retrieval, contributing to learning and cognition, and deciding what to focus on. The thalamus is part of neural networks involved in emotional states and the affective aspects of experiences like pain. It transmits motor signals, shaping conscious movement. I rest my case. It is almost as if the biological brain was designed to fit the Xzistor brain model. So I will argue that the Xzistor mathematical model of mind can provide robots with emotions that are principally no different from those of humans. Note I say principally. Consciousness. Some neuroscientists say that if we can give a robot emotions, it can be deemed to possess a level of consciousness. One such person is neuropsychologist Professor Mark Solms, author of The Hidden Spring. He has articulated that emotions, or more precisely affective feelings, are the source and foundational basis of consciousness. I have tried to demonstrate to you today how we can provide robots with emotions, real subjective feelings. I will let you be the judge if such a robot with emotions will also be sentient. To conclude my talk today, I would like to read to you the conclusion of a comprehensive journal paper I have asked Gemini to generate for me. This is what Gemini says about the Xzistor brain model. The Xzistor mathematical model of mind represents a significant paradigm shift. By adopting a top-down, functional, control theory perspective, it offers a coherent framework that integrates emotion, cognition, learning, and consciousness. Its core contributions, emotions as homeostatic loops, the combinatorial generation of feelings, embodied awareness, and the threading model of thought, resolve long-standing conceptual challenges. The model's validation against neural correlates and its implementation in robots demonstrate its biological plausibility and computational viability. It stands as a powerful tool to unify fragmented research and provides a concrete blueprint for building a new generation of AI, not just intelligent machines, but sentient, emotionally aware agents that are truly like us. This approach may well be the key to demystifying the brain and unlocking the future of artificial general intelligence. Thank you for your time today. I hope you found this talk interesting. Please click on this link to access all the additional information mentioned in this talk. I will now open the floor for questions. The first question we have is from Ollie in the Southern meeting room. Ollie's question is, how much of your time do you still spend working on this AI model? For this question, we will cut to the Southern for video coverage.
I'm lucky. The slide back, for instance, has been existing forever, so it's all done. I mean, I patented the mathematical model of mind in 2002. Yeah, so at that stage, it was complete. I had to write a patent specification. So after that, it was more a matter of sharing it with people and getting into Barney's on X, and people, refusing to accept that it's possible. Very interesting debates we have on X. And with the neuroscientists I work with, we write the odd paper now and then. They help me with that. We've done some podcasts with them. So at this stage, I'm not changing anything. I don't need to change anything anymore. Now it's more a matter of bringing the message to others and saying, is anybody interested in learning from this, either to understand the brain better or to build a new type of AI? So I don't take a lot of time. I browse through X, talk to people. There's nothing to develop. I'm not programming anymore. My whole robotics lab has been reduced to just a single PC. And I don't build robots physically anymore. It'll all be simulations. If it picks up, it might be in the future, we might build some new interesting ones. If there's some interest from people out there, we would certainly be happy to collaborate. But at the moment, it's a hobby, and it takes very little time. Like I said, just on weekends, it keeps me off the streets.
The second question we have is from Kyle in the Southern meeting room. Kyle's question is, in all your programming and the tests and experiments you've run, have you observed any unpredictable behaviors because of emotions? Something you didn't explicitly program, but something that resulted from the emotions you have programmed. And for this question, we will again cut to the southern for video coverage.
It was unpredictable until I realized why it looked that way. So for instance, I taught my little robot to move in its learning confine, to move to a food source and to eat the food source, so to speak. And then I put a cactus in its way. And the little robot bumped into the cactus and felt severe pain. And remember what happens, it creates stress. So the next time the robot had to walk to the food source, it saw the cactus and it wouldn't go to the food source. Now I can see on its internal states how its hunger is picking up and getting more urgent and more urgent. And you can see it wants to go to the food source, but it's the emotion of stress over the cactus is still stronger than the food. So you run into a situation, and then I take the little robot and I say, no, hang on, I'll help you out here. I'll see you can move around the cactus. Let's do this again. We can move around the cactus to the apple. And again, let's move around the cactus to the apple. Do you feel better now? Or are you still scared of the cactus? And then the robot will move again and still get stuck when he sees the cactus. And that is when I realize, almost like a psychological problem, the stress from the cactus is just too much. Even with repetitive examples of how you can move past the cactus, the fear of the cactus remains so strong. So in that case, when the robot looks away, I switch it off and I switch it on again and I start training it again. So you do get some states. And once again, it normally maps back to human psychology. You see this parallel with human psychology. Well, of course, it's just too intense. They can't get the memory out of his brain because the memory is rated so high because the stress was so high. And then eventually you can get a situation where a robot will kill itself because it's too scared to move to the food source or the battery charger in the case of a robot. Interesting question. Thank you.
The third question we have is from Jake, who is online. Jake's question is, how long have you been working on this? And what sparked the idea in the first place? For this online question, there is no video coverage.
That is a very difficult and deeply personal question, but since you've asked, I'll give you the short version. When I was a young engineer, I was pretty confident that I will be a successful engineer. The family and society expected of me of going to work in the morning, returning back in the afternoon, get married, have 2.3 children, and be successful, and in 20 years' time, get a golden pen from my company. This was not enough for me. I wanted another challenge in life. And I was thinking about two things, the origin of the universe and solving the human brain. And a little voice inside me told me, the origin of the universe is too complicated. I haven't got enough time in my life to solve that one. But I had a hunch that if we look carefully at the human brain and decompose it in its complexity into more simple mechanisms, we could get there. And I think there's no reason to be mystified by emotions. These are mechanisms, physical mechanisms. And if we can understand functioning, how they work in the brain, we should be able to replicate them in machines. And from that point onwards, I started thinking about it. I built a small simulation, very simple simulation, to start testing my initial ideas. That simulation, I moved then into this little Lego robot. And from that point onwards, I got to a point where I actually patented my brain model, the Xzistor mathematical model of mind. And then I became very confident that it's working properly and started sharing it with people later. But it has been 30 years, a big adventure, yeah.
The fourth question we have is from Kyle, who is online. Kyle's question is, you talked about this way to program emotions into robots and machines. Have you tried changing the gains on the variables or flipping the positives and negatives? For this online question, there's no video coverage.
It's a very good question. This model, this mathematical model of mind, has taught me a lot about unfavorable emotional states like depression, anxiety, autonomic stress. And what struck me was that something like depression I could simulate in these robots. So by going into my functional mechanisms and pulling a few buttons and changing a few variables, I could subject a robot to a permanent state of depression. And that was quite concerning. But then I learned exactly how this could also help us understand depression better, anxiety better, and all the negative states. But it is interesting that you can simply turn two wires around in this model. And what was very pleasant to the robot now becomes very unpleasant. And what was very unpleasant becomes pleasant. So those body states only get value in terms of avoiding or pursuing them because of how you learn through operant conditioning, how you learn that a feeling is good or a feeling is bad. On another day, those butterflies in the stomachs, when you're nervous, could be a highly pleasurable feeling. It's just when we use it and how we use the homostat learning and the reinforcement to teach you the meaning of those states. So I hope that answers your question.
The fifth question we have is from Rob, who is online. Rob's question is, in a practical application, how do you prevent a robot with a mathematical brain from choosing self-preservation and giving up on a defined mission? For example, think of a rescue application where an Xzistor robot with hazard perception and training would have a higher likelihood of success, but potentially deem it too dangerous to continue through damaging situations. This is an online question, but towards the end, we will cut to the southern for video coverage.
It's a very good question. And I sort of on X the other day, I tried to make contact with Elon Musk. And I said, why do you want to send people to Mars? I've got these Xzistor robots. And we can send them over there and they will learn how to maintain themselves, how to get sunlight, to charge their batteries, and how to stay safe and stay out of the sandstorms and all those things. And I'm still waiting to hear from him. I'm sure he's just writing out the check. But it's interesting. Rob, we can give it a hierarchy where it will have certain preferences and instincts. We can give them a complete set of instincts, which will say, you pursue the human's mission. Go on to Mars and explore, take photographs. But when the sandstorm comes, you must get back to the den or the charging station where you will be safe and out of the weather.
So we can give it instincts where it will override what it learns. So it's got emotions, it wants to do stuff, but it could instinctively say, for instance, I will not hurt a human. Whenever I see a human, I will preserve myself, but never at the cost of the human. And I've written quite a few papers explaining this principle. And this is why I make a fundamental claim against the Xzistor mathematical model of mind, to say that it is physically safe, as opposed to the new LLMs, the large language models that everybody is so concerned about. This is built into the physics of the robot. So it's got its ethics and its safety built in. And it will never override, it cannot override something which is built into instinct. You learn things, you do things selfishly, you do things to serve your human tutor, but in the end, we've got these instincts which just say, you will always act kindly to a human, you will always be protective of a human. And it's a very important question that people are asking more and more in this day and age. So thank you for that question. Well, thank you guys. Thanks for your time again today. I really enjoyed it. And perhaps next time I can not talk about emotions, but explain to you how Xzistor robots think and solve problems. Thank you for your time.
Thank you for joining us for this Infinity Talk. Feel free to send questions or feedback about this groundbreaking AI framework to the presenter Rocco Van Schalkwyk. Please use the contact details provided on this link page. Thanks again, and remember, never stop being curious.